Good evening, everyone. I want us to start. We began looking at cyclic groups last Thursday. We looked at how to find generators, especially if you are given an additive group, Z star. We saw how to find generators for this group. And we also saw how to find generators for this multiplicative group. So that is what we went through last Thursday. We defined what a cyclic group is. We said a cyclic group is a group that has one or several elements generating it. So we saw examples of cyclic groups, and then we went ahead and found generators. So today we want to go a step further again. We still looking at cyclic groups, and this time we are looking at the direct product of cyclic groups. So supposing we have two cyclic groups and then we get the direct product. For instance, supposing this is a cyclic group, the additive groups will always be cyclic. So supposing I have this additive group and I have this other additive group and I get the direct product. So the question is, what are the generators for this group? So that's what we'll be looking at today again. And we could also we'll also get to know when do we say that this group cross this other group are cyclic. So when do we say they are cyclic? Even for this one, we will want to find out. It's not always obvious. It's not always obvious that when you get one cyclic group and then the Cartesian product with another, for instance, this is cyclic and this is cyclic. It's not obvious that this product will be cyclic. So we'll want to find out when is this product cyclic. So that is one thing we'll be answering in today's lesson. And again, supposing this is cyclic and this is cyclic. So when do we have this product being cyclic? That is again the other question we'll be answering. And after answering those two questions, the other question we'll be answering is, now supposing this direct product is cyclic, what are the generators? And again, for this one, what are the generators? So those are the questions we are supposed to answer in this today's lesson. And then get a program that can tell us when those two are, when the direct product is cyclic. And of course, that program will be giving us the generators for the cyclic group. So I've said that the direct product of cyclic groups, of course, there must be cyclic groups. Group A and group B must be cyclic. Then we get the direct product. And I'm saying that direct product is not obvious that it will be cyclic. So we'll be finding out when is this direct product cyclic. And this concept is important in cryptography and other mathematical fields. For instance, in cryptography, the direct product of cyclic groups will be used to create more complex groups for cryptographic protocols. Of course, when you're making these protocols, you want to have something that is more secure. So instead of just going for one group like Zn, you want to complicate that and have a direct product of two groups so that your protocol or your cryptographic system is secure. So that is one way of ensuring that it's secure. For example, the crypto systems employ direct products to integrate the security features of several smaller groups. So I have several smaller groups. You see the direct product, we are doing two groups just to as an example, but you can have even 3 groups, or even 4, or even 5, getting the direct product, or even 10, as many as you may want, get the direct product. The concept is just the same. And to do that, again, you are ensuring that your cryptographic system is secure. So therefore, understanding whether, and this is the first question we'll be answering, understanding whether a product is cyclic or not is very important to us, because it will influence the design of our security protocols. Of course, you may want to use a group that is not cyclic. There's no problem. But if you wanted to use, again, a group that is cyclic, is good for you to know, depending on what you want in your cryptographic protocol. So you may want to use cyclic groups or non-cyclic groups. Now, what are the properties of cyclic groups? The first property here, I've said, just a minute, let me admit. So the first property here, I've said that given, if you're given group 1 and group 2, and both of them are cyclic, and let's say that the order of the first group is N1, and the order of the second group is N2, and then the order of this product will be this product. So again, of course, we've learned about getting the order of an element and getting the order of a group. So the order of a group, of course, means the number of elements in that group. So what we are saying is, what this question is just, what the first point is saying, is that if group 1 has N1 elements and group 2 has N2 elements, the product of these 2 groups would have this number of elements. Would have this number of elements. So that is what, this is the first property, and we'll be looking at that. Of course, when we looked at, the first time we looked at direct product, we must have seen that. Now, the second property is that, supposing I have group G and group H, and supposing that both of them are cyclic. If the order of G is N and the order of H is M, then this direct product, I've said, is not obvious that it will be cyclic. Although the groups coming in are both cyclic, it's not obvious that the product will also be cyclic. So the only time that the product is cyclic is if and only if these 2 orders, M and N, are relatively prime. If the 2 orders are relatively prime, then the direct product will be cyclic. So that is, we've already answered the first question that we were to look at. Although we'll be looking at examples again, just to emphasize that. So what I mean, therefore, is that this group is cyclic, and this other group is cyclic. So for this product to be cyclic, I look at the orders. This group has 5 elements. This group has 7 elements. 5 and 7 are relatively prime, and therefore this group will be cyclic, the direct product. This direct product group will be cyclic. But look at this one. This is cyclic, and this is cyclic. But 8 and 4 are not relatively prime. Although the 2 groups are cyclic, their direct product is not, because the 2 orders. So you see, this one has 8 elements, and this has 4 elements. And so the GCD of 8 and 4 is not 1. That's what I mean by relatively prime, for those who are new doesn't mean relatively prime. We say that two A and B are relatively prime if their GCD is 1. So for this case here, you can see that 5 and 7, their GCD is 1. So since their GCD is 1, the product of these two groups is cyclic. But these two here, their GCD is not 1. And therefore, the product of these two groups, although the groups are cyclic, their product is not cyclic. So we've answered our first question. We were to look at when do we say that direct product is cyclic? When do we say? So we say that we do that. We say that they're cyclic if their GCD is 1, the GCD of the orders. And we've already said that the examples above, I've used two groups. But we can have several groups. We can have several cyclic groups multiplied together. And so when do we say that these several groups are cyclic? So for us to consider these several groups, we consider them pairwise. I've used the word pairwise. That means I will consider the order of this group and the order of this group and see if they're relatively prime. If they're relatively prime. Then I'll consider this group with the next, see if they are relatively prime, and so on. Then the next pairwise, I pair 2, 2, 2, 2. Then I can also pair this and that. So you pair two groups and see if you find that all of them, after pairing all of them, you find that they're all relatively prime. Those pairs, if all the pairs are relatively prime, then we say that the product, the direct product, will also be cyclic. Will also be cyclic. So that's why I said the direct product can be extended to more than two cyclic groups. For instance, if you have G1, G2 up to GK, which are cyclic, and if their orders are N1, N2, N3, and up to NK, then we will say that these groups are cyclic when we consider the orders pairwise. Consider the orders pairwise. See if the pairs are relatively prime. And I repeat, relatively prime means we are finding out whether the GCD is 1. So if the GCD of those orders is 1, 1, 1, every time you pair 2, you find the GCD is 1. Every time you pair 2, the GCD is 1. It means that the product will be cyclic. That is what that means. So I think we've answered that question. And again, you can look at these two examples. This example says, determine, okay, of course we can say that these two are cyclic. But now I'm bringing another concept, the concept of generators. Can we find, because we said that if a group is cyclic, it means it has a generator or several generators. So the question is, of course, we know that this is not cyclic. This is not cyclic because the orders, this one has 2 elements. This one has 2 elements. The GCD of 2 and 2 is not 1. So this is not cyclic. I can see that. I can see that the GCD of 2 and 3 is 1. So this group here is cyclic. But that is not the question I'm answering here. The question I'm answering is, what is the generator? What is the generator? Now, this is an additive, these are additive groups. The generator is very easy. These are additive groups here. These are additive groups. Of course, we know the elements here. Now, Z2 has the elements 0, 1. That is what we mean by Z2. Z3 has the elements 0, 1, 2. That's what we mean by Z3. And for those who are new, what we mean is this. When we talk of Zn, the elements there are 0, 1, 2, all the way up to n minus 1. That's why I've said Z2 has element 0, 1, because n is 2. 2 minus 1 is 1. So it goes from 0 to 1. And for this one, n is 3. 3 minus 1 is 2. So the elements are from 0 to 2. Now, so what do we mean by Z2? And again, I'm doing this for those who are new. What do we mean by Z2 cross Z3? What we mean is the same as 0, 1 cross 0, 1, 2. That's what we mean. And this, we just do it the same way we used to do. We multiply the elements here by the elements here. The elements in here by the elements here. So when we do that, the 0 and 0 will give us 0, 0. That's the first element of that group. The second element of this group, 0 and 1 will give us 0, 1. The other element, 0 and 2, will give us 0, 2. That's the other element. Now we have exhausted 0 and the other, combining 0 with these other elements. Now let's combine 1 with each of the elements. Combine 1 with that. We have 1, 0. Then we have 1, 1. Then we have 1, 2. This is 1, 2. And this is 1, 1. So this is the elements of the group. These are the elements of the group. I'm just doing this for those who are new. Now, how many elements are they? How many elements are they? So when we answer the question, how many elements are they? That question is answering what is the order of this group? What is the order of this group? The order of this group is 2 times 3. 2 times 3, which is 6. And in fact, when you count, you'll find there are 6. Let's count. 1, 2, 3, 4, 5, 6. There are 6 elements. Now, what was the question? What was our original question? I've just gone into those details just to assist those who are new so that we move together. So that when we talk of Zn, Z2, they know what we mean. When you talk of Z3, they know what we mean. When you talk of Z2 cross Z3, they must know what we mean. We mean it's a group where we're taking 2 groups and multiplying. And when we multiply, the elements become a combination of those elements. Just the way we've been combining. Now, so the question is, show that Z2 cross Z3 is cyclic. Of course, we've already seen that it's cyclic. All of us, we all see that it's cyclic because we've said that it's cyclic if the order of the elements, if the orders are relatively prime. If the orders are relatively prime, and I'm emphasizing that word just for those who are new again, the word relatively prime means the GC, this one. Now, so 2 and 3 are relatively prime. So this group is cyclic. So the question is, what are the generators? Of course, the easiest generator for an additive group is just 1, 1. That is the easiest generator. But of course, we will want to find out how to find all the generators. That's what I want to do so that we come up with a group, we come up with a program that gives us all the generators. But this is the easiest generator for an additive group. This is an additive group. You've not seen a star anyway. You've not seen a star. When you say star, that means a multiplicative group. So multiplicative group, the generator will not always be 1, 1. But for an additive group, 1, 1 will always be a generator. And of course, there'll be other generators. There'll be other generators, but we shall look at how to find other generators. Let's just prove that 1, 1 is a generator. A generator is an element that will generate all the other elements. So all the other elements are this. These are all the other elements. Can one generate these elements? That's the question. So we want to add one to itself several times. That's what we were doing last time. We want to add it to itself several times and see whether every time we add it, we get an element of the group. So when you add it once, you have 1. When you add it to itself once, just once, without even adding. So 1 once, you have the first element of the group. So we have generated this element. Now let's add it to itself twice. That means 1 twice, or you can write it this way: 1 plus 1. This is what I mean. So the way we add these elements, you add the first elements, you get 2, but the first elements are coming from this group, mod 2. So 1 plus 1 is 2 mod 2. 2 mod 2. And these are the elements. Again, the sum is 2. This time, mod 3. Now, what is 2 mod 2? What we ask ourselves, if 2 are to go into 2, what will be the remainder? That's what we write. So 2 into 2, the remainder is 0. What about 3 into 2? The remainder will be 2. So we've generated this element. Generate that element. We want to see if we can generate all the elements. Now we've added 1 twice. What about 3 times? What about 3 times? What do you get? And of course, this 2 times has given us, this is just the same as 0,2 plus 1. Because these are giving us 0,2. Now, so 0 plus 1 would be 1. Mod 2. What about 3? No, 2 plus 1. That gives us 0. We generated this element. That was 2 times. Of course, we are going to do it 6 times because the order of this group is 6. 2 times 3 is 6. 2 times 3. So we are going to do it 6 times. And we must have generated all the elements on the 6th time. Now the 4th time, 1. 4 times this is 4. Mod 2 is 0. And then 4 times that is 4. Mod 3 is 1. So we've generated the element 0, 1. The fifth time, adding 1 to itself 5 times. 5 times 1 would be 5. Mod 2. So if 2 are to go into 5, the remainder will be 1. And then 5 times 1 is 5. Mod 3, if 3 were to go into 5, the remainder will be 2. So we've generated this element. Then the last time, 6 times, 1 to itself, 6 times. 6 times that is 6, mod 2, the remainder is 0. And then 6 times that is 6, mod 3, the remainder is 0. Generate the last element. So 1 is a generator. 1 is a generator. And I've said that for an additive group, an additive direct product group, 1 will always be a generator. But the question is, are there other generators? Of course there are. That is what I want us to look at. But before that, I've said check to see whether the following 6 elements generates. So you check all the elements. But this style of checking will be a bit long because you want to check this, check that, check this, and see which one is generating. That is why I want to come up with an easier way of finding generators, and that easier way would then assist us to write the code. Of course, I've said that 1 is a generator here. So that is how we write it. The question is, does 1, 2 generate? So you try 1, 2, see 1 to see whether it generates. And when you do that, so you find that it also generates. The group. Now, this other group, we had already disqualified it from being a cyclic. And the reason was that when we looked at, by looking at the orders 2, 2, the orders 2, 2, the GCD is not 1. And that therefore tells us that it's not cyclic. But the other way that I used here, how I did it, I tried all the elements to see which one will generate. Of course, 1, 1 is supposed to be a generator. So I tried 1, 1, and it could not generate all the elements. 1, 1 just gave me this element, gave me this element, gave me this element. So they were repeating. You can see 1, 1, 1, 1, 0. So it's only generating 2 elements. It's only generating 2 elements instead of generating 4, because 2 times 2 is 4. This group has 4 elements, but 1, 1 can only give us 2. So 1, 1, once 1, 1 fails, no other element would generate. Once 1, 1 fails. Now, so what is the easiest way of getting generators? Before that, I looked at this other example. I think I decided to look at this example, then I combined the 2 reasonings together to then come up with the easiest way. There's a point here. I said, notice that in the example above, this example was cyclic because the orders were relatively prime. That is, the GCD was 1. However, this one was not cyclic because it was not, the orders were not relatively prime. So we can simply, the easiest way, therefore, we can simply apply a GCD of orders to determine if a group is cyclic. To determine if it's cyclic, we can simply use that. That is the easiest way. But now the next question is, how do we determine cyclic generators? That is our next question. And that's what we'll be answering. But before we answer that, let's look at this group. Now, the 2 groups are Z5 is cyclic, and Z7 star is also cyclic. And of course, yes, Eugene, can see your hand is up.
Yes, I have a question.
Yes.
You could simply tell that the group was cyclic just by checking the order of the groups. So why did you have to find the generator?
Yeah, you see, the definition of a cyclic group is one that has a generator. And generators are important, especially when you're looking at primitive roots. When you'll be looking at primitive roots and look what other crypto systems like the Hellman crypto system, we want a group that has a very huge generator, one that has a higher generator. So it's the issue of the generator is very important. You want to see is that does this group have a higher generator for security reasons? Those are what we call primitive roots. Because the primitive roots are looking at, in terms of crypto system, they're called primitive roots. Looking at does the group has a primitive root, and is it big enough to allow security? You see, the essence of this unit of action is targeted to ensure that we have those crypto systems. We want to come up with crypto systems, want to test the security of those crypto systems, and so on. And so everything we are doing is geared towards that, not just an issue of identifying that it's a cyclic or not. Of course, identifying that a cyclic is important because we want to know, are we dealing with a cyclic group or not? And then when it comes to the issue of primitive roots, then we have to learn how to get them, those primitive roots or the generators, the elements which can generate the entire group. And why I also showed that is that in some cases, it will not be easy to tell if a group is cyclic, like in the case we are in now. The case we are in, the one we are looking at, Z5 cross Z star 7, you see, this one you cannot easily tell whether it's cyclic or not. And so again, the issue of determining that generator becomes important for you to tell whether it's cyclic. Like this one, you cannot tell. But if I remove the star, you can tell that the group is cyclic. If I remove the star, that is for an additive group. But for now, if I add this star, it cannot tell that it's cyclic. But the only thing you can tell here is that Z5 is cyclic. Z5 is cyclic, and we can also tell that Z7 with a star is cyclic. And of course, last Thursday we said that once it has this star, a multiplicative group, they'll all be cyclic except those where n equals to 4k, where k is greater than or equal to 3. Except, greater or equal to 2. Except for those. But so like this one, you see, this 7 cannot be written in terms of 4k. So of course it is cyclic. But if it was Z star 8, this is not cyclic. This is not cyclic because 8 can be written in terms of 4k and k will be 2. Now, so the issue of getting whether it's the generator is important because of the issue of the primitive roots, and of course, some groups, again, it cannot be easy to tell whether they're cyclic. Like the case we are in now. Yes, Eugene, have I answered that question? Are you okay?
Yes.
Okay. Now, this case that we are in now, we have two groups which are cyclic. Is their product cyclic? That is the question. So that for this one, we must get the generator to tell whether it's cyclic. And for this one, it's not obvious that the generator is 1-1. I said the generator of the 1-1 for both additive groups. If both of them are additive groups, the generator, obvious generator of the 1-1, and of course there will be other generators. For this one, 1-1 is not obvious generator. Now let's see what Z5 means. Z5 is the set comprising of 0, 1, 2, 3, and 4. What about Z star 7? Z star 7 is the group comprising of 1, 2, 3, 4, 5, 6. And of course, again, for those who are new, we say that Z star N comprises of 1 and other elements which are relatively prime to N. Other elements which are relatively prime to N. For this case, since N is prime, all of them, all these elements are correct. But supposing it was 8, the only elements which are relatively prime to 8 are 1, 3, 5, and 7. These are the elements which are relatively prime to 8. So Z star 8 will be this. Z star 10 will be elements which are relatively prime to 10. The elements which them with the 10, the only common factor is 1. So we have 1, we have 3, we have 4 not, 5 not, 6 not, 7, 8 not, 9. These are the elements which are relatively prime to 10. Now, back to the question. This group has 5 elements. The order is 5. Now, the order of the group is 5. The order of this other group is what? 1, 2, 3, 4, 5, 6. Is 6. So we expect the direct product to have 5 times 6, which is 30 elements. We expect the direct product to have 30 elements. So can we find one of the elements which can generate all the 30? Can we find an element which can generate all the 30? And then I come in with my easier way of getting the generators. Now, what are the generators of Z5? We had talked about this. The generators of Z5 are elements which are relatively prime to 5. These are the elements. The elements which are relatively prime to 5. What about the generators to Z star 5? I've written here these two are the generators, 3 and 5. Are the of course, we had looked at this one earlier. We looked at this one last Thursday, how to find the generators of these groups. How to find the generators of these groups. Now, so the generator of Z star 7 is 3, 5. Of course, you can try 3 and see whether it generates all the elements, all these elements. You can try 3. So when you try 3, you multiply it by itself. So 3 once, just be 3. 3 twice will be 9 mod 7, that gives you 2. Then 3 times is the same as 3 twice times 3. But 3 twice is 2. When you multiply that by 3, you get 6. And then 3 4 times will be 3 thrice times 3. But 3 thrice is 6 times 3, that will be 18. 18 mod 7. If 7 were going to 18, the remainder will be 4. And so on, and then you get 5. So 3 generates, again 5 will generate. You can use the same method we used last time to find generators, so you can listen to the video and so on. Now, so I've obtained the generators of this, and then the generators of this. Then since I'm getting the direct product, to find the generators of the direct product, I get the product of this. I get the product of that. So what I'm doing, what I'm saying is, the first group has these generators, and the second group has the generators 3, 5. So what are the generators of the product? I would combine 1, 3, and you can see it's a generator. I can combine 1, 5, and it's a generator. I'm done with 1. I can combine 2, 3, it's a generator. Combine 2, 5, it's a generator. Combine 3, 3, it's a generator. Combine 3, 3, 5, another generator. Combine 4, 3, it's a generator. Then 4, 5 is a generator. So all these are generators. So if you just wanted one, you can pick one out of that, supposing you want to use one. But all these are generators. And you have seen how I've done it. And you can use the same method even for the previous example and get the generators. So once you get the generator for this group and the generator for this other group, then combine those. So this one can give all the 30 elements, can give all the 30 elements of this group. Just a minute, just a minute. Okay, let's continue. Now, so you see, we learn how to write those codes, programs to do this, getting generators for us, because for security reasons, when you are dealing with these crypto systems, we want to deal with the bigger groups. The ones I'm dealing with here, the smaller groups, just for education purposes. I'm dealing with the Z5, Z7, and so on. So we'll be dealing with the groups with the very big orders, where doing the manual calculation of the generators will not be easy. But now you need this manual calculation for you to tell how to then write the code. Because the easiest way I found of writing the code to give me the generators for this group, one is to write the code to get the generator for this group, which we did last week. So I have now, I now write a code that has a part for doing the generator for this first group, then another part for doing the generator for this other group. So I have a part that does the generators for this, and then a part that does the generator for this other group. Then after that, I have a part now combine the elements. Now combine the elements the way we've been combining to get this. So I have a part to do that multiplication, and you come up with the generators. So this, the ones we do in class dealing with these small examples are supposed to just guide us on how to write the code that can give us now generators for bigger groups, of course, which we're supposed to be dealing with in terms of crypto systems for security reasons. Now, so I've now tried to verify. I was verifying that 115 is a generator. And when I did that, it's supposed to give me all these elements, because we said that that group has 30 elements, and these are the 30 elements. This what we are seeing here are the 30 elements. Now that is one way. One way is to multiply it, to multiply this 115 30 times and see whether it gives you the 30 elements. That is one way, but it's the hardest. The easiest way is to understand what the word order means. The word order, when we talk of the order of a group, what do we mean? The order of a group, we mean the number of elements. So this group has the order of 30. Now, so an element would generate these 30 elements if its order is also 30. An element will generate 30 elements if its order is also 30. But if its order is not 30, it cannot generate 30 elements. If you can generate these 30 elements, then we say it's a generator. It's a generator. Let me just again repeat. Let me repeat. I'm talking about, let me talk about a smaller group. We talk about a smaller group. A smaller group, and I want to talk about Z8. Z8. Z8 has 8 elements. So a generator to this group should be one which can generate these elements. Yes. Yeah. Niko class, eh? Ndakupigia. Now, so I want to talk about Z8, and I'm still explain the issue of the generator. We know the generators to this group are elements which are relatively prime to this. You know that 1 would be a generator, 3 would be a generator, 5 would be a generator, 7 would be a generator, those which are relatively prime to this. But now, what do we mean when we say 3 is a generator? The order of this group is 8. So the order of 3 must also be 8. The order of 3 must also be 8. That means we would add 3 to itself 8 times to give us all the elements of this group. I think that is now clear. We said this group is of order 8. So the generators of this group must also have order of 8. So coming back to our question, the group in question has order 30. So it means the order of the generator must also be 30. What is the order of an element by definition? The order of an element is the integer k whereby a raised to k will give us the identity for if the group was multiplicative. If the group was multiplicative, the order of the element A is k if a raised to k is 1. And if the group was additive, the order will be k if a multiplied by a is 0. Now, so we have the two groups here. We have one which is additive and one which is multiplicative. So we've said that 1, 5 is a generator. So it means its order is also 30. So that means 30 multiplied by 1 should give us 0. And of course, that is what it does. 30 multiplied by 1 is 0. Mod 5. Mod 5. And then this other element was from a multiplicative group. So it will be 30, 5 raised to 30. 5 raised to 30. And so for those who've done the fast powering algorithm before, 5 raised to 30 mod 7 is 1. That I used fast powering algorithm. Fast powering algorithm. Of course, we did that manually, and we did that also with we also did that with the code. So 5 raised to 30 will be 1. So this, of course, is the identity for this group. So it means this are proof, therefore, that 1, 5 is a generator. So that is one way. You can prove it by raising this to 30 and seeing that you get the identity, or multiplying 1, 5 30 times and seeing that it gives you 30 elements. Now, I want you to recall how we've obtained the generators. And I want to do one more example of how to get the generators, and then we'll go straight to the code and implement that, the method that we are learning of how to get the generators. I'm back to the additive groups. Every time I'm trying to make them bigger. This is an additive group. This is an additive group. Want to get the generators. Of course, we know that 1, 1 is a generator. But we want to find the other generators because we are interested with, when you talk about primitive roots, we want to choose one of the largest, of course, for purposes of security. We know that it has several generators, but we don't want the easiest because this one anybody can tell, anybody can try, anybody who is trying to use brute force, trying each of the generators can always begin with this. Now, so we want to choose one of the generators, of course. So we want to know how many are they, and choose one of them. And again, I'm still answering the question Eugene was asking, why we were to get the generators. Because you may be interested with one of the generators to use it in your crypto system. Now, so the generators of this group are elements which are relatively prime to 11. This group, Z11. So the elements relatively to 11 are all these. So all these are generators. What about the generators to Z12? These are elements which are relatively prime to 12. They are 1, 5, 7, and 11. 3 is not. And 2 is not. 4 is not. So these are the only elements which are relatively prime to that. Now, what are the generators for this group, therefore? I just combine 1 with each of these. So I'll have 1, 1, 1, 5, 1, 7, 1, 11. 1, 1, 1, 5, 1, 7, 1, 11. And then combine 2 with each of them. 2, 1, 2, 5, 2, 7, 2, 11. 2, 1, 2, 5, 2, 7, 2, 11. And so on through with each of these 3, 1, 3, 5, 3, 7, 3, 11. 3, 1, 3, 5, 3, 7, and so on. So all these are generators, this group. All of these are generators. Now, again, how are we going to write the code? How are we going to write the code to give us the generators? So you can see that these are additive groups. So if we are doing additive groups, we will write a code that will give us a generator to this group. Just as the way I've done. Then write a code that will give us a generator to this group. Just the way I've done. Then write a code that will now give us the product. And then, no, it's just one code, of course, it's just one code. So we are writing a part, there's a function. There's a function, let me use the word function of the code. There's a function that is giving us the generators this group, and then a function that is giving us generators this. So this, of course, this is just one function because this is an additive group. But this one function, we'll tell it to give us the generators that, then give us generators that. Of course, we'll be having we'll be having a part, a function that will be asking for the generators of Z11. So you have a function that is calling on this other one to give it the generators of Z11. So you have one that is just generating the generators. So, but we have one that is calling it on it, calls on it, give me the generator of Z11. Then it calls on it again, give me the generator of Z12. And then we'll be having another function that is now taking these generators here and getting their product. And then, of course, you have the main function that is now printing those generators. So those are the functions we'll be having. So we must have one that is just, and that is how the easiest way. That is the easiest way. One function to give us the generators of the groups. There's one that is calling on it, calls on it, generators of Z11, then this one gives. Generators, and then it stores. Generators of Z12, and then it's given, then it stores. And then there's one that is now taking those generators and getting their product. Then they have the main function that then prints. Now, so what follows therefore is that a code, that Rust code, and the following Rust code implementation finds generators. A direct product of two. I began with the additive groups. So the primary use of this code is to identify pairs of elements that generate the entire group, which can be useful in various mathematical cryptographic applications. This part I'm just reminding you that this group is cyclic, and is a cyclic group of integers mod n. Integers mod n, this is what I mean. And I mean, when I say integers mod n, is what I mean. 0, 1, 2, all the way up to n minus 1. So mean by integers mod n. So you have this direct product, whose generators we want. So in this program, I've defined this structure, Zn, Zm. This one represents the group. Zn represents this, and Zm represents this group. So here it is. Just defined my n and m. I've said n is U32. Of course, we mean 32 bits, and m is also 32 bits. And of course, U means we are dealing with positive numbers. If you wanted to deal with the negative, we will talk of I32 and I32. And of course, you can increase this to 64 or 128 if you want to deal with bigger numbers. If you want to deal with bigger numbers, you can change. You can change wherever there's 32, change to 64. Or if you want to deal numbers bigger than 64 bits, you can change to 128. And if you want to deal with the numbers bigger than 128 bits, you can change it to big units. So we can always do that. Now I have this part to implement Zn, Zm, and I've said Zn stands for our additive group Zn, and then, so this is the direct product. I've used this abbreviation. This is just direct, standing for the direct product. Now, so I have this function. And then I have this function. The one I've said that it's find generators. Then I have this function. Is a generator. This one is to find generators. Then this one is a generator. And of course, I'll tell you what it will be doing and how it will be doing that. And then after that, we have the main function. So you have those three functions. Okay, let me share the code first of all. You see how it works. Give us generators. You can see the code, is that okay?
Yes.
So the first part, I just said where I'm defining my n, I want it to be 32 bits, of course, a positive 32-bit numbers, and then type 32-bit m, and then implementing this this Zn Zm stands for Zn cross Zm, that direct product. Then I have this function. This function, of course, I have n and I have m, and then once it gets n and m, it gives me the direct product with, so this is what it gives and Zm. But now I'll explain how it's working. Then the main thing is this: find generators and see how it begins by taking the mutable generators. These are mutable. So first of all, it creates an empty vector. This empty vector here is where it will be storing. So it will be storing the vectors. So it begins with the empty. It gives you an empty vector. And that is why it says mutable, because it's empty at this point, but then it will get to change, be changing, be getting generators. So it gets the first generator, goes there, the second generator goes there, and so on and so on. And for I in 0 to n, 0 to n, yes, so you know what n is. N has been defined here. So n could be 8, could be 10, could be 13. So what is this one is saying? So you know 0 to n is 0, 1, 2, 3, up to n minus 1. Up to n minus 1, 0, 1, 2, 3. So I is any element within that range. I is any element. So I can be 0 to begin with. Then I will go to 1. I will go to 2. I will be changing. I will be changing. Then J is now defining 0 to M, the other group mod M. And again, from 0 to M. So within that range, it says, if ij is a generator, Then push that I, J into this vector. So what this one is doing is this. Supposing I have my I is 1 and my J is 2. It's checking to see whether 1, 2 is a generator. So if 1, 2 is a generator, it pushes it here into this. And then at the end of it, after pushing all of them, it will have generators. But now, the one which is doing the whole thing is here. The one which is doing the whole thing is here. This is the one which is identifying the generators. Then after identifying generators, you see it's called here. This one is calling on is generator. At this point, you can see is a generator. So for instance, I want to look at 1, 2. So this one combines 1, 2. After combining 1, 2, it sends a message to this to find out whether 1, 2 is a generator. So this will now check to see whether 1, 2 is a generator. Once it finds that 1, 2 is a generator, this one gets the message, the 1, 2 is a generator, and then pushes it here. Then this one talks about, what about 1, 3? Then calls on is a generator function, 1, 3. So this one finds 1, 3 to find out whether 1, 3 is a generator. And it does, and we shall be looking at how it does to find out whether 1, 3 is a generator. Once it finds 1, 3 is a generator, so this one has it pushes, generator push it into this empty vector. Now, this one now looks at, what about 1, 4? And then this one calls on this with 1, 4. Then this one checks that 1, 4 and finds that 1, 4 is not a generator. So this one has nothing to push at this time, and so on and so on. That's how it's doing. Once that is done, so we'll be looking at how this one will be doing that, all that, to find out whether elements are generators. So I hope you know the roles these are doing. So the main thing are between these two functions. That's the main thing. And this one does not have a lot of role. It's just combining the elements. Combine 1 and 2. After combining 1 and 2, it asks this part to tell us whether 1, 2 is a generator. Then this does that part. And after doing that, then communicates this. This one finds if 1, 2 is a generator, then it pushes it there. What is the main function doing? The main function, first of all, begins with letting this be a group. So the group, I've said N is 11 and M is 12. So this is where you enter what you want. So I'm dealing with the Z11, Z12. And then after inputting these two N and M, after inputting N and M, it calls on find generators function. It calls on find generators function. So find generators function is this one. So it does call on find generators function to find generators for the group Z11, Z cross Z12. So the find generators function, once receiving that call, it starts combining I and J. I in this range, 0 to N minus 1, and J in this range, 0 to M minus 1. So 0 and 0, where I is 0 and J is 0, calls on is generator function. Is generator function is here, considers to see whether 0 and 0 is a function. Finds that 0 and 0, no, whether 0 and 0 is a generator. Finds that it's not. So there's nothing to push and so on. So let us ask it to give us the generators for this group. Cargo run. It has given us generators. And it has said the generators for Z11 cross Z12 are the following. All these are generators up to here. All these are generators. It has done that in 0.02 seconds, very fast. Let us change this and make it 32, 23. If we make it too long, it may take longer. Let's say 40 and see. But there will be so many generators. We will not see all of them. There will be so many. Yeah, there will be so many generators here. All these are generators. Now, so very first, let's see how the code works, how it works. Of course, I've already explained how it's going to work, those two main functions. Those two main functions. Now, the first part I've said we define the structure Zn, Z11. This represents the direct product. And the first part represents Zn, and the second part represents Zm. So this one contains the fields. The field are just the numbers that we're going to work with. Where n is the field, and we're saying that this field is U32. U32, and this other one is also U32. And then implementation. So this one just contains the methods they're going to use. So this function, we have this constructor new, this part creates a new instance for this group with the n and m. For example, if I insert 11 and that, then it creates this group. So that part is just doing that, creates this group. But then we just call it Zn, Zm. Yeah, but it understands that part. This stands for this. It understands it stands for that. Now let's now go to our main functions. Our main functions. Of course, we have seen where the whole thing is beginning. The whole thing is beginning from the main function. So you've inserted your two numbers, 11 and 12. And this main function, since it knows it cannot do this, it calls for the function that can do it. The function that can do it is find generators function. It calls on find generators function and then waits. Then the find generators function receives the call. It's here now, it's here. It has received the call to find generators for Z11 cross Z12. It has found that call. It understands the elements in Z11. It understands that Z11 has elements 0, 1, 2, all the way up to 10. It also understands the elements in Z12 are 0, 1, 2, all the way 11. It knows that 0, 0 can never be a generator because there's no number of times you can multiply 0, 0 to get a different element. Combines 1 and 1. So you can see what it's saying. For I, these are I's. These are I's and these are J's. Those are J's. For I in the range 0 to n, And for j in the range 0 to m, self is just m, because we are dealing with the m, that is 12. And in this case, self is 11, which is n. Now, for the i's in this range and for j in this range, now, if self is if self is a generator, so it begins by calling. What you now get, for instance, combine 1 and 1, where I is that and j is that. So I is 1, 1. Calls on is a generator to consider 1, 1. Then the is generator function is here. So it will be considering that, and we'll be seeing how the calculations. Then after is generator function has considered this, if this is a generator, it says generator push ij. So ij is pushed into that empty vector. Then once that is done, that is 1, 1 has been pushed, then it asks, now combines 1 with another element, 1, 2. So now it says, if is generator ij, so I is 1 and j is 2. So it's calling for this function, to consider if 1, 2 is a generator. Now, so this function now does that role. If it finds that 1, 2 is not a generator, there's nothing to push. That process continues. So this one does not have a lot of work. It doesn't have a lot of work. It's just asking. It's asking. And then once it gets a result, it pushes into the vector. Now, once it has considered all the elements, at the end of that process, it will have all the generators. So you'll see it has all the generators here. It has all the, at the end of that process, it has all the generators. Very fast, let's look at how this one works. Now, this one is a bit long, but it begins by, this is the one that is finding if elements are generators. Now, so it begins by letting the it begins counting at 0. Of course, what are we saying? What we are saying is, for an element by generator, you add it, these are elements, it has been given 1, 1. It has been given 1, 1 to find out whether 1, 1 is a generator. The first thing what it's doing, it wants to add 1, 1 to itself several number of times. Not even several number of times, because it knows that, for instance, Z11 because Z12 has order 11 times 12. This is the order. So it will add these elements to itself this number of times until it finds the identity element. No, not this number of times. It will add it to itself until it will add this element to itself until it gets the number of elements. At that time, if the count, by the time it gets the identity element, if the count will be equivalent to this, it will declare that element a generator. That's why you're seeing there's a count here. So it begins a count at 0, adds the element to itself. That is a count 1. Adds the element to itself. So when the 1, 1 comes, the count is 0. No, before 1, 1 comes, the count is 0. Now, when 1, 1 comes, then it counts 1. Then adds it to itself. That is, it says count is 2. Adds to itself, the count is 3. Now, if the count, at the count of 4, the addition has given us 0, 0, 1, 1 is declared not a generator, because it was expected that if it's a generator, the count will go up to, this is 132, 12 times 11, 132. The count will go up to 132. But the count has gone up to 4, so 1, 1 is not a generator. So it informs the one above. The one above now asks, what about 1, 2? So this one does the same thing again. Count is 0. So 1, 1, 2, 1, 2 comes in, the count is 1. Then adds 1, 2 to itself. That is the second count. Then adds again another 1, 2 to that result. The count is 3. Adds 1, 2 to that new result. The count is 4. Supposing this process continues and 0, 0 is obtained at the count of 132, then 1, 1, 2 is declared a generator. So that process then happens for all the elements. That process happens for all the elements. So that is how this code will then be working. That's how that code will be working. And of course, that is what we are seeing here. That's what we are seeing here. For instance, let me just explain very fast. 1, 2 has come in. 1, 2 has come in. So at this time, x is 1 and y is 2. So it's x and that is 1. Now, so what it then does, it adds this to itself, then and so on. So there's plus a and plus b, and they have been defined. Okay, x began with 0 and y began with that. Yes. So this one is a and this is b. So the sum continues. This summation continues until the count is 0, until you get 0, 0. X becomes 0 and y becomes 0. They began with 0. It began at 0, so you add until you get 0, 0 again. And then you find out what the count was. Now, so later on, you look at these notes. I already have them, the explanation. You look at that explanation, you see already here intact. Thank you. Thank you.